Okay, so 7.1 is the properties of the normal distribution. So let's first define the density function. The probability density function, also called PDF, not the program, but this type of function. This is an equation used to compute probabilities of continuous random variables. In order for it to be a PDF, a normal type, then it needs to satisfy the following two conditions. So number one, the total area under the graph of the equation over all possible values of the random variable must equal to 1. So the total area underneath the graph for this equation over all possible values of the random variables must equal to 1. So it's related to probability. Remember we said the sum of all probabilities must be 1. Very similar, it's just in terms of a function and a graph. Okay. But it's all related. Number 2, the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. I think the first few questions I'll probably ask you, is this a normal distribution? Is it a PDF? Okay, let me think of an example here. Suppose you, let's say, flip a coin. Three times. That'd be too many. Create a probability for x equal to number of heads. We're going to create a graph, a probability density graph that focuses on the total number of heads out of the 3 flips. And of course, the outcomes have to be either 1, 2, or 3 heads, right? So this would be number of heads. Up here would be the probability. That makes sense. So last class we figured out how to calculate probabilities. So you agree that there's 8 different ways you can flip the coin, or 8 different outcomes total of flipping 3 coins. I'll go ahead and give them to you, I guess. You can get 3 heads. You could get 2 heads and then tails. You could get heads and then tails and then heads. You could get heads and then tails, tails. You could get triple heads. Or sorry, triple tails. Tails, heads, heads, or tails, heads, tails. 1, 2, 3, 4, 5, 6. I'm missing one more. What did I miss? Tails, tails, heads. Yeah, I think you're right. So this is every possibility. Okay, so how many ways can I get exactly 1 heads? Yeah, I see 1, 2, 3, right? So 3 out of 8 would be the chance of 3 heads. Or sorry, exactly 1. Okay. So I'm gonna put 1 up here. So 1/3. I'm sorry, 3 out of 8. I'm sorry. What is that? That's a decimal. It's almost 0.4, right? 0.5 is right here. So 0.4 is about there. Zero 0.375 would be the chance of 1 heads. Okay. And I'll go ahead and write that. X equal to 1 would be 0.375. What's the probability of x equal to 2, where x is the number of heads? Exactly 2. 1, 2, 3, right? As well. Or is it 4? I think it's 3. 1. Yeah. Okay, let's probably leave exactly 3. It's just the 1, correct? So 1 out of 8 as a decimal. .125, so down here somewhere. Although I did mess up, I forgot about 0. You could get 0 heads, right? That is a shame. I'm gonna have to redraw that. Oh, I'm sorry. How many ways can you get 0? Just one way out of the total, which is 8. So let me just tack on 0. Because if you don't do every outcome, it will not add up to 100%. So 0, 1, 2, 3. There's a 0.125 chance of 0. There is a 0.375 chance of 1 and 2. And there's only a 0.125 chance of 3. So P of 0 would be the same as P of 3. That'd be the distribution of your experiment. If you add up the area of every single rectangle, it will equal to 1. And the height of each one is not greater than 1. It's sorry, it's not. It's greater than 0, and the total is equal to 1. So that satisfies 1 and 2. Okay. Well, let's talk about normal distributions. The idea makes sense, though. Is it okay? Yeah. Here's a definition. A continuous random variable is normally distributed or has a normal probability distribution if it has a relative frequency histogram in the shape of a normal curve. So normal is one of the most common curves that you'll see when you're collecting data. Like for example, if you were to collect everyone's height or weights in the entire campus, you'll see eventually a bell curve histogram, which means it's normally distributed. And if something is normally distributed, then you can do all kinds of stuff. You can make a lot of assumptions. And so it's a great thing to have when you're trying to do predictions, analysis, or any kind of statistics. So if you have it, great. If you don't, then you're gonna have to figure out if it's a different type of distribution. But it looks like this here. Oops. Here. So as you collect more and more data, you can see the curve is smoother as smoother. When the population is bigger, eventually you get that curve. This is the IQ data. So the center being the average being will have the highest frequency, right? That's common. So average intelligence, average IQ would be the center. Right? As you can see, like more and more data, it tends to highlight. Being above 100 would be above average intelligence. Further you go, the more rare it becomes. And then we can estimate by the standard deviation how small this group is. It's like super genius people. It would be very rare. And then over here is working like I would say maybe tens of conditions that are bringing them way below average. Okay. But as you can see, I was saying way before, that means having a population is below average. That's a big issue. And so when you're at the store and you see a bunch of weirdos, and it makes sense. It's a lot of them. Go to Walmart, you'll see it. Anyway, a lot of things are normal. Hence the name. Let's see if there's anything else that we need to write down before we move on. I think that might be it. Okay, let me give you a bunch of properties. Properties of the normal curve. So number one, the normal curve is symmetric about its mean. Mu. Lowercase mu. The Greek letter. Not a cat sound effect. No, it's backwards. Okay, two. The mean is equal to the median, which is equal to the mode. The normal curve has a single peak. and the highest point occurs at x equal to mu. Number 3. The normal curve has inflection points at mu minus sigma, lowercase sigma, and mu plus sigma. Number 4. The area under the curve is 1. Number 5. The area to the right of mu is 1/2 because it's symmetrical, right? So if I only look at half the total, it'd be a half. So the bottom part and the top part are both halves, left and right. Okay, 6. As x increases, without bound, gets larger and larger. So picture that bell curve, right? The graph. You're going all the way to the right. X is getting larger and larger. You saw how if that was in terms of IQ, the IQ goes to 500. That curve goes and approaches 0, right? Becomes less and less likely that exists. But let me put that in their terms. The graph approaches but never reaches the horizontal axis. As x decreases, outbound, the graph also approaches the x-axis. Basically, what I was saying earlier, if it gets too positive, too negative, the curve comes down, approaching 0. So this is my attempt at drawing this bell curve. So as you keep going on the x-axis, you keep going to the left all the way this way. Grand cap. So if we're talking about height or weight, right? Being this extreme weight, like 10,000 pounds, you found is very unlikely. Population goes to zero. Same thing for as the weight goes way over here or height or whatever. It's too small and becomes unlikely. Or that group equals stack. Maybe there's one person that weighs 1 pound out there, I don't know. But it's unlikely. Does that make sense? Okay. So there's a lot of stuff you can say about the or with the bell curve. Apparently there's a 7. I didn't realize that. Okay. What do you part 7 on the next page then? You guys okay on this page? 7. I think we mentioned this before a little bit. The empirical rule. Approximately. %68 of the area under the normal curve is between x equal to mu minus sigma and x equal to mu plus sigma. So if you go out one standard deviation in both directions, you will have 68% of the population. Okay. If you go out 2, you'll have approximately 95%. So 95% of the area under the normal curve is between x equal to mu plus 2 sigma. And x equal to mu plus 2 sigma. (99.7% of the area). I'm going to shorten this, is between x equal to mu minus 3 sigma and x equal to mu plus 3 sigma. I'll give you one last picture and then I'll let you work on the homework. Okay. I don't know he did that. I know he was a big guy in pre-cal, but he also did contributions to statistics. Apparently he was his name is Abraham Demois. I'm sure if you took pre-cal, you did that Demois theorem. If not, it's just whatever. But he was on the committee for the debate of who invented calculus between Newton and Leibniz. So it's kind of cool. But anyway, down here, this is the percentage we've been talking about. We've mentioned this before. We had one that was kind of general. This is a specific distribution. So if your data is normal, then you can make all these assumptions. So if we're talking about height or whatever, if I know that the average is 5, 8, whatever that is, 5, 10, I don't know. And if you know the standard deviation, then you know that if someone does it well in 6.2, based on their standard deviation, we'll figure out if that's what we hear something pretty rare thing. Statistically, once you pass 5 and 10, it drops to about around here. Just private. But assuming the entire world competition. Of course, the opposite is true. Once you start going below 5 feet, it becomes pretty deep. Okay. But if you have 10 deviation, you have the average, you can make these conclusions. That makes sense. It's pretty powerful for research and all kinds of things. All right. And I'm sure you've noticed we've entered a world of data and AI. So statistics is a big deal, and it's used part of the algorithms, part of the machine learning, all that stuff. If you're interested in that field, I would study statistics and do programming. If you want to go into AI. All right. Feel free to work on your homework. Let me take roll. Dylan, you here? No. Isaac? No. Sonia? Jalen? Bianca? Christabel? Antonio? Elizabeth? Amanda? Kaylee? Addison? No. Caitlin's not here. Clarissa? Sebastian? Abigail? Giselle? Aaliyah? No Aaliyah? Okay. Mariana? Jennifer? And Emma? No, oh, there you are.